So here I want to talk about terminating system and the whole concept of replications and how we can use that to get a better sense of the performance of the terminating system. So I want you guys to please open model 5.3, the very last model that we did from chapter 5. I think we finished this model 2 weeks ago. So this is model 5.3, the one in which we did staffing as well. So this is the one, if you remember, in which we created a bunch of variables. For example, the new people that can work on technical support for product 1, 2, 3, the new salespeople, and so forth. So this is the model in which we try to calculate the total cost of staffing and the delay of the customers in the line, and also we calculated the percentage of the rejected calls. And our idea was to see how we can increase the number of staffs to improve performance of the system and so forth in terms of the number of rejected calls per hour and so forth. So I want you guys to please open this model. This is the model of the call center. And if you remember, that model was a terminating system. So what is the definition of a terminating system? So a terminating system is a model in which we start the model from a specific initial condition. For example, here we started the model at time 0 every day, and with 0 calls or 0 customers in the system. So that was the initial condition for every replication. And then we continued running the model for 10 hours. And then after 10 hours, we did not let any new customer to come to the system. However, we continued running the system till everyone who is in the system gets the service and leaves. And those are the terminating conditions that we put in the run setup window. So terminating condition is that run the simulation for 10 hours, 600 minutes. And after we pass this 10 hours, if the number of trunk lines that are busy, which means the number of customers that are in the system is 0, that means no customers in the system anymore. Everyone who came in the system got the service and left. Then we can stop the simulation. Also, we made sure that we do not let any new customer to come to the system after 10 hours. And to be able to do that, we define an arrival schedule. So in this schedule, we define the schedule for the arrival of the customers. So how the rate of the arrival of the calls or customers change over time. But at the very end, remember, we had the very last line in which we said the arrival rate is 0 for, let's say, another 2 hours. After we are done with putting all the schedules for the different arrival rates in the day, in the 10 hours of the operation, then we say that, okay, then no customer comes in the system maybe for another 2 hours, 1 hour, and so forth. So, and then we run the simulation, and that does not let any new customer to come in. And if we continue the simulation, this will just continue. So what I want you guys to do is to change the very last line, and instead of just 2 hours, just saying that, oh, the arrival rate is 0 just for 2 hours at the end, we want to write infinite. Okay, so what this will do is that it will guarantee that after the 10 hours of simulation time is done, then for infinite amount of time after that, the arrival rate is going to be 0. So this will guarantee that no entity will enter the system after the 10 hours of the basically working time are done. And one other thing that we discussed 2 weeks ago was the whole concept of replication. Just saying that if I asked you to tell me what is the percentage of rejected calls in 1 day, in 10 hours of operations, for example, in 600 minutes of operation, what is the number of customers that came to the system or number of calls that came to the system and got the service and left? What is the working process in the system? What is the average waiting time in the system? So if I ask you these questions, so what you can do is to just run the system for one replication, which is just 1 day, and report the numbers to me. Okay. This would be equivalent to observing what happens in this call center in just 1 day. However, that 1 day is just one sample or one instant of what happens in this system in each day. if we want to have a more reliable reports and results, we want to be able to collect data for more than one day. So we want to be able to, for example, observe what happens in this call center in a month, in 30 days, and then at the end look at what has happened in each day, and average of all these days, and look at the average of all these days and then report those numbers. And that's why the whole concept of replications came to the picture. So we said, okay, why not we'll run this same simulation model for 10 replications. So we changed the number of replications to 10. I do not change anything else in the run setup window. And remember that for the replication length, I also do not need to specify any time, because this is a terminating system. After the 10 hours of the simulation, the working time are over, and when there is no call in the system, no customer in the system stops automatically. So I don't need any specific run length at all. So I'm going to run this simulation for 10 replication. If we look at the results, we see that, so here we see on the top, it shows 10 replication. So here, for each one of these numbers that are of, or statistics that are of interest to us, it shows the average. And what is this average? So for example, here it says that for the technical call, for the technical support calls associated with product 1, their average waiting time in the system is about 12 minutes. So the unit of time is minutes. So on average, they have been waiting in the system for 12 minutes. For the sales calls, they have been waiting in the system on average 18 minutes. Why do we have the term average? Because these are the average of the waiting times for calls, for example, type 1, product type 1, across all 10 replications. And that's exactly what we see here. If you want to see the results of each replication, we can go to the replications, click on the replication side on the left-hand side. And then here, if we open this, we see the results for all 10 replications. For example, if I look at tab replication 1, we see here replication 1, I can look at these numbers. So these show average of waiting time for each one of these entities. So that's what I see for replication 1. And for the half wait, you see there is nothing reported here. It's insufficient, okay? So that's basically just because we ran the simulation for 1 replication. And here I just see the results of 1 replication. When I run the simulation for 10 replications, that's the one that I can see in category overview. What I see here in the average, these numbers is the average of all 10 replications. However, as you can see in the half wait, we see some results. We no longer see insufficient and things like that. And this is the half wait of the 95% confidence interval for each one of these numbers that were reported. Okay, so if you look at the, for example, working process for technical support calls related to product 3. So on average, there are 6 of them, 6 of those calls in the system, and the half wait is 0.5. So what does this mean? So it means that I have written the numbers here. The average is 6.01 and the half wait is 0.5. That means that on average, there are this number of calls type 3 in the system. So this is the average of all 10 replications. So I also here have a half wait. And what does that helps me to do? The half wait helps me to construct a 95% confidence interval. So I show it with CI, confidence interval. And so the confidence interval has a lower bound and it also has an upper bound. To be able to construct the lower bound, we have average minus half wait, which is 5.41. And then for the upper bound, we have average plus half wait. And this is going to be 6.61. On average, for technical calls that are related to product 3, we have had about 6 of them in the system. However, this number, which is related to working process for calls related to product type 3, can changes between 5.41 and 6.61. So this is a 95% confidence interval that simulation automatically calculates for us. So that means, so what does this confidence interval mean? So if I run the simulation, obviously for 20 replications, for 100 replications, for maybe another 10 replications, this average that I obtain will be different, right? So this is the average across all replications. If I run it for 20 replications or 100 replications, or even you guys in your own computer for the same 10 replications, you may have a different average. So obviously this average will change if I change the sample size, which is the number of replications. So this confidence interval tells me that if I change the size of the sample and look at the average again, with 95% chance, this interval from 5.41 to 6.61 will contain that average that I will obtain. And it is important for us to not only look at the average of everything that is of interest to us, but also a sense of the spread around the average. And the sense of the spread around the average in these 10 replication is given to us by the size of the confidence interval. So for example, if I go to the very last one, here in the output, if you remember, we in the user specified, if you click on the user specified, here on the output, we calculated two things. One of them was percentage of calls rejected, and the other one was total cost, which was related to the cost of all the staff and call of the people waiting and call of the rejected calls and so forth. So if I consider this average and reported half width, I can develop the confidence interval. So average minus half width gives me the lower bound of the confidence interval, and average plus half width gives me the upper bound of the confidence interval. So that means percentage of rejected calls across these 10 replications or these 10 samples that we got shows me that on average 11% of the calls got rejected in a day. However, if I take more samples, more replications and so forth, I expect this average to change. However, if I just change the sample size or the number of replications, maybe run it for 20 replications, 200 replications, another 10 replications and so forth, obviously the average across the replication, average of percentage of rejected calls across the replications would change. However, this confidence interval that I have developed, then the interval from 9.74 all the way to 12.8, this interval will contain the percentage of rejected calls that I will get in a day, even if I change the sample size. So if you are going to report the results of any terminating system, you should report not only the average, but also a sense of the confidence interval. The confidence interval that Arena reports itself automatically is a 95% confidence interval. However, you may want to look at some 99% confidence interval or 90% confidence interval and so forth. So we want to see how potentially we can get those results. So to be able to do that, let's go back to the model. And here in the model, so let's go to the statistics that we calculated. So let's assume we want to do these things for the percentage of rejected call or total cost, the statistics that we calculated. So let's go to the statistics data module in advanced process panel, and let's click on the total cost that we calculated. And here we chose total cost to be an output. What does that mean? That means this total cost based on this formula that we define is calculated at the very end of the simulation. And the same for the percentage of rejected call, we define that as an output as well. So what we want to do here is that we want to tell the simulation that when all these 10 replications are over, save the result of all these 10 replications for the total cost and save it in a file. We call it an output file. We can give a name to this output file. So I'm going to call it base total cost. Okay, and I call it base total cost because this is a scenario, this is a base case scenario in which I have not increased the number of staff, I have not done anything. So this is the base case scenario. So that's why I call it base total cost. And also at the end put .dat. So put this extension, that way this is saved as a data file, and then we can read this data file later. So what happens is that when the simulation run is over, this data file is created in the same place that you have saved your model. This data file is created in the same folder, and this data file contains the result of all 10 replications. So when you have the result of all 10 replications in a data file, then you have the flexibility of doing a lot more with those data files. So here we press OK. And we are going to do the same for percentage of rejected calls. So here for the percentage calls rejected, it still is defined as an output. It's calculated based on this formula we entered. However, I'm going to save it also in a data file. So after all these 10 replications are done, I want these data files to be the one that contains the results of all these 10 replications. And I'm going to call it base calls reject. Okay. And dot DAT. Okay, so this data file also will, when we run the simulation, this data file also will be created in the same folder in which you have saved your model. So base calls rejected and base total cost are the two data files that I want to be created. I'm going to run the simulation. If you go to the folder in which you have saved your model, you see here I have two data files. One of them is base calls rejected .dat, the other one is base total cost .dat. And both these data files were created after I ran the model for 10 replications. These two data files contains the results of all 10 replications. So if I want to read these data files and do additional calculation on top of these 10 replications, for example, calculate a 90% confidence interval or a 99% confidence interval, I can do that. However, we have to use a different software for reading these data files. These softwares are also from Arena, the same company that has created this simulation software. However, the name of the software is Output Analyzer. So if you search and so if you search for Output Analyzer, here you see, so this is the icon, this is how it looks like. If I open it, this is how the Output Analyzer will look like. So these are some of the menus that we will use. So here in the graph menu, you can use this to plot a bunch of graphs and histograms using data associated with these 10 replications. Here in the Analyze, there are a bunch of options also. If you want to develop confidence interval for the means or for comparison between the means and standard deviations and so forth, you can do that here. So what I want you guys to do is to go to Analyze, and what we want to do is to develop confidence interval for the mean, and we want to use just the classical confidence interval. If I press that, then this window opens, and here I have the option to pick the data that I want to play with. So here I click on the add because I want to pick the data file that in which I have the data associated with these 10 replications. Click add, and then when this window opens, I press browse, and here I can see this is the same folder in which I have saved the model. Here is where I see the data files that were created. The two data files are base calls rejected and base total cost. So here I'm going to click on the base total cost, for example. And so that's the data file that I want to use to calculate the confidence interval on the total cost across these 10 replications. What I want to do here, instead of just specifying a specific replication, I want to pick lumped, the option lumped. And what happens is here when we pick lumped is that it uses the result of all these 10 replications to calculate the confidence interval. And then we press OK. And then here we can give a name as well. We can say that, for example, if for the confidence interval, I say, okay, I want to develop a 90% confidence interval. Here I can say the 90% confidence interval for total cost. Okay, so that's what I want to put for the name of the graph that is going to be created. And then I press OK, and here this confidence interval will be generated. So here it tells me that on average across these 10 replication, this is the average of cost per day, and this is the lower bound, and this is the upper bound of the confidence interval. We can also see the results here. So this is the same average across all these 10 replications, and the standard deviation across all these 10 replications is given here as well. And the size of the half width, the 90% confidence interval half width. So this is the size of the half of the confidence interval, however, a 90% confidence interval. And this is the minimum and maximum value for the cost that we have observed across these 10 replications. And at the end, you see number of observations or number of replications or number of samples is basically 10. Here's how we can do further analysis on the results of these 10 replications with respect to the total cost. If you want to develop, for example, other graphs, you can do it here as. We can do that for the percentage of rejected calls as well. So again, let's go to the analyze. I want to develop the confidence interval on the mean, a classical confidence interval, and here the data point that I want to use is going to be the one related to rejected calls. And I want it to be lumped again, press OK, and I want it to be 90% as well. And here I want to change the name, which you can see the name appears here, 90% confidence interval for total cost. So I wanted the title to be 90% confidence interval for total cost and rejected calls, or percentage rejected calls. And when we press OK, you see the second confidence interval. So the first confidence interval is for total cost, and the second confidence interval, which is very squeezed, basically is related to the percentage of rejected calls. And the reason that you see it this way is that I tried to put these two intervals in one graph. One of them has a scale in the order of thousands. One of them has the scale in the order which is less than 1, and that is why you see these two graphs together in a way that basically makes it impossible to understand what is happening in the next one, in the percentage of rejected calls. So just keep that in mind. If you want to put confidence intervals in the same graph, just make sure they are comparable in terms of the scale. Just make sure they are comparable in terms of the scales. If one of them is in the order of thousands and one of them is something less than 1 or in the order of 10, then one of them turns out to be really, really narrow. So for this one, if I want to do this, I go back to the confidence interval and I remove the first data set. I remove the first one, delete. And this is basically the confidence interval that I want to report only for percentage of rejected calls. So I only keep the data for percentage of rejected calls, and I also want to report a 90% confidence interval, let's say, and then I press OK. And then you see now, then this confidence interval for the percentage of rejected calls is now very nice and easy to read. So that tells me that on average, 11% of the calls were rejected, and this percentage of rejected calls can vary between 10% all the way to 12.5%, given the fact that the standard deviation across all these 10 replications is 2.14, and the size of the half of the confidence interval is 1.24. So you can basically look at these, use a standard deviation if you need to for other purposes and so forth. Okay, let me go back on the developing confidence interval for the mean again. So I delete this data set that I have and I want to add a new data set. This data set is going to be the base total cost. And I'm going to pick the lump, and let's assume I'm going to develop a 95% confidence interval. So the 95% confidence interval for the total cost. And this is going to be the value, okay? So this is the average, and this is the half of the confidence interval. So obviously, when we take a sample of size 10, so here I ran the simulation for 10 replications. So I have only a sample of size 10. And based on the values of this sample, obviously the length and the standard deviation that I see between these 10 samples, the size of the confidence interval is specified. We know that if we increase the sample size, we get more and more sample about regarding the cost per day. So the average that we observe is more and more reliable, and we expect the size of the confidence interval to shrink down. And one of the questions that may be asked is that, okay, what is the right size, what is the right number of replications so that we come up with a reasonable size for the confidence interval? So for example, here the average is around 20,800 and it varies between 20,200 and 21,000. Okay, so however, sometimes the length of the confidence intervals are very wide, and in that scenario, the average is not very reliable. If you're using the average for some planning purposes, that average is not reliable, because if we can increase the size of the sample or number of replications, we get more and more data regarding the cost of the system per day. And when we develop the average, the confidence interval that we will obtain will be narrower as well, and that's a good thing. So one of the questions that you may ask is that, okay, what is the reasonable value for the number of replications? So usually we start with some arbitrary number of replications, let's say 10 replications that we have done in this scenario. With that replication, we get a sense of the average and the size of the confidence interval. How do I get a sense about the size of the confidence interval? I have the size of the half bit, or size of the half of the confidence interval. If I multiply it by 2, that would be the size of the whole confidence interval, right? And if that seems large, given what you are trying to estimate, then we can try to see how we can shrink the size of the confidence interval. So here, for example, I may want to know that what if I want to shrink the size of the confidence interval into half? In that scenario, what should I do? Okay, let me go back to my iPad so that I can explain to you how this will work. Okay, when we take a sample of size n, so n is the sample size or the size of the replications. In this scenario, n is 10. Okay, so we took n sample in each one of these n samples or n replications, we look at the total cost per day. And the reason is that we want to get an estimate for the cost per day in this system. Okay, so we ran the simulation in n replications. We look at the total cost per day in each one of these replications. And at the end, we reported the average of the cost across these 10 replications. Okay, so this is the average of the cost per day. And also to get a sense of the variability about around this average, we also reported the lower bound and upper bound of the confidence interval. And let's assume this is a 95% confidence interval that we developed, okay? So the formula that we have from statistics, the lower bound of the confidence interval is calculated when we have the average. If you want to find the lower bound, we have to deduct z alpha over 2 sigma over square root of n, and to calculate the upper bound, we have to add the same value to x bar, and that would be z of alpha over 2 sigma over square root of n. So this gives the average, this gives the lower bound, and this gives the upper bound of the confidence interval, right? And the sigma here is the standard deviation of the whole population. What is the population here? If I had the possibility to look at the performance of this call center across all days in which this call center has worked, if I had all of that data, the sigma will show standard deviation of the daily cost across all those days, okay? Obviously, I don't have the access to such data. So if I don't have then sigma, I'm going to use S instead of sigma, and S is the standard deviation of this 10 samples or 10 replications that we calculated. So S is the standard deviation across the 10 samples or 10 replications. So if I replace sigma by S, then the formulations for the confidence interval is going to go from the lower bound, which is going to be minus T S over square root of n, and the upper bound is going to be x bar plus T S over square root of n. Okay, so this is going to be the new formula for the lower bound, and this is going to be the new formula for the upper bound. And this is the same average that we have. So then the size of confidence interval which is upper bound minus lower bound, is going to be upper bound, which is x bar plus t minus lower bound. And so the x bars cancel each other. The size of the confidence interval is going to be 2 times t s over square root of n. So this is the size of the confidence interval. Then the size of half of confidence interval is going to be the half of this value, which is going to be t alpha over 2 s over square root of n. Then what happens most of the times is that we may get some sense of the desired size of the confidence interval or the desired size for the half of the confidence interval, which I'm going to show it with notation E just for the sake of formulations. So the desired size for the half of the confidence interval, if it's given to me, I'm going to show it by E. Then the question is that how I can get to the desired size for the half of the confidence interval. Of course, given the fact that this is a formulation for the size of the half of confidence interval, I have to somehow play with this formulation. So obviously, I'm not going to change the value of the t, because the value of the t, which is coming from t distribution, represents the confidence level or the size of the confidence in the interval. And I don't want to change the confidence level. I still want to have develop a confidence interval that has 95% confidence level. So I'm not going to change the value of the t. The S is not going to change as well, because that's the standard deviation of the cost that has been calculated across 10 replication. I have no control over S. And the only thing I can play with potentially is N, which is the size of the replications or the size of the sample. If I want to reduce the size of the confidence interval, or if I want to reduce the size of the half of confidence interval, that means I have to find a way to reduce this expression, to reduce the size of this expression. And for this to happen, the only thing I can play with is n, and I have to increase the size of n. And the reason I have to increase it is that n is in the denominator. If I want this whole thing to decrease, I have to increase the value of n, which is in the denominator, and as a result, this whole expression will decrease. And intuitively, this makes sense as well, because increasing n means increase the sample size, increase the number of replications. If I increase the number of replications, I come up with more values that are estimate of the cost per day. If I have more and more samples of the cost of the cost per day, the average that I'm going to calculate is going to be a more reliable number, and the confidence interval that I'm going to calculate is going to be a narrower size and a better confidence interval. So then the question is that now that I know E, the desired size for the half of the confidence interval is T S over square root of n. If I know the desired size of the half of the confidence interval, what is the sample size, or what is the number of replications that can potentially gets me to this desired E? If I use this formulation and I do the calculations, I can see that n equals to T S over E to the power of 2. So this is the formulations that we need to know. So if you give me the desired size for the half of the confidence interval, I can tell you what should be the number of replications. Using this formula, I can tell you what should be the number of replications or what should be the size of the sample to get me to somewhere close to this desired size for the confidence interval. So now let's go back to the example that we had and see how we can use this formula to find out what is the right number of replications that can get me a desired size for the confidence interval or for the half of the confidence interval. Okay, here we see that from the result of output analyzer, the size, after running the simulation for 10 replications, the size of the half of the confidence interval is 674. Okay, so let me write this in this Excel file. So the size of the half of the confidence interval is 674, and that's basically E, the size of the half of the confidence interval. As a result, the size of the confidence interval itself is basically 2 times this number. Right, so that's the total size of the confidence interval, which is basically upper bound minus lower bound. Now let's assume I want a new size for the confidence interval, and I want the new size of the confidence interval, let's assume, to be 60% of what I already have been able to obtain. So I want to shrink the size of the confidence interval, and I want the new size of the confidence interval to be 60% of what's already there. And so this is going to be the new size of the confidence interval. And as a result, the new size for the half width in this confidence interval is going to be half of the new size of the confidence interval, obviously. So this is, I'm going to call it new E. So this is the new E that I'm going to get to. So the current value for the E, which is the size of the half of the confidence interval, is 674. And I want to get to 404. I want the new size for the half of the confidence interval to be 404. And the question is that what is the number of the replications or the sample size that can get me this size for the half of the confidence interval, or this size for the whole confidence interval. So based on the formulation that we just talked about, to be able to calculate the size of the half of the, to be able to calculate the required number of replications, I need to know the standard deviation. I need to know the t-value, and I need to know the new E. Okay, so the size for the half of the confidence interval. I know the value of new E, or desired E, is this number. The value of the standard deviation, so the only thing that I have for now in terms of the standard deviation of the cost, estimated cost per day, is the standard deviation of these 10 replications that I already have run. When I ran the 10 replication, the standard deviation across these 10 replications was 942. I'm going to put that here, 942. And then the other thing that I need is to calculate the number of replication is t value. To be able to calculate t, I need to know alpha over 2, and I need to know n minus 1. So n minus 1, n is the sample size, and the sample size previously was 10. 10 minus 1 is 9, so n minus 1 is 9. For alpha over 2, I need to know first the value of alpha. Alpha is calculated by calculating 1 minus 0.95. And 95 is basically represents the 95% confidence interval that we have developed. So that's where we got this 0.95 representing the confidence level in the confidence interval that we have developed. 1 minus 0.95 is 0.05, and then alpha over 2 is going to be 0.05 divided by 2. That's going to be 0.025. So with these two values, I can calculate the value of the t-value from the t-table. So this is the t-table. The values on the top row shows the alpha over 2 in our scenario is 0.025, and the values on the first column shows the degree of freedom, or n minus 1, which in our scenario is 9. So if I look at row associated with 9 and the column 0.025, the t-value that I have to use is 2.26. So I put the t-value here. And then n, which is the size, the number of replication, or the desired number of replication based on the formula that we just looked at, is t multiplied by standard deviation divided by e, desired e, the whole thing to the power of 2. That's 27.7, or about 28 replications. So if I run the simulation for 28 replications, I expect to obtain a better estimate of the average, and I expect the size of the confidence interval to shrink from this value to this value, and as a result, the size of the half of the confidence interval goes from this value 674 to 404. That's what I expect. So now let's go back to the simulation and see what happens if I increase the number of replications. So before I run the simulation for 28 replications, let's go to the statistics data module. Here you see the total cost. So click on the total cost statistics, and here I don't want the results of 28 replications to be rewritten on the data file I already have. So here I say new confidence interval. And that's going to be the new data file that is going to save the result of these 28 replications. I also change it for the percentage calls saved. It's unnecessary, but I'm just going to do it for consistency. So I also want the percentage of rejected calls to be also saved in this new data file. And then I'm going to change the number of replications from 10 to 28, and I'm going to run the simulation. After I run the simulation for 28 replications, I come back to the output analyzer here, and I want to create this new confidence interval that I have calculated. I don't want to get rid of the previous confidence interval that I had. I want to add the new confidence interval to the same page. So I'm going to keep the previous data file base total cost, and I'm going to add this new data file that we just calculated. The new data file that we just calculated after I ran the simulation for 28 replications is this new confidence interval total cost. And I'm going to pick LUM, and if I run that, again, a 95% confidence interval, what I'm going to observe is this one. So the first confidence interval is associated with 10 replications. The second confidence interval is associated with 28 replications. And as you can see, the results are here as well. The first one is related to 10 replications. The second one is related to 28 replications. And the size of the half of the confidence interval went from 674 to 399, which is very close to 404, which was our target value for the size of the half of the confidence interval. So here, basically what we observe is that after running the simulation for 28 replications, I got a more reliable value or estimate for the average cost per day, and I was able to shrink the size of the confidence interval to 60% of what it was. And that's good, because when the size of the confidence interval is narrower, that means the average that I have obtained is a more reliable number. So if I need to use this number for any planning purposes, I can trust this average. Now let's go back to the simulation model. And here, so we look at the cost, for example, a 90% confidence interval and 90% confidence interval for the cost and for the percentage of rejected call on the base case scenario. Now let's assume we want to compare those total costs for one day or percentage of rejected calls in one day. We want to compare those with the scenarios where we increase the number of staff. And if we click on the variable in the basic processes panel, click on the variable. These are some of the variables that we had defined when we wanted to develop this model and we wanted to add more staff. These are some of the variables that we defined. The new sales was the variable that we used in the defined schedule to tell that what if we hire additional sales people for some specific hours during the day. New tech 1, new tech 2, new tech 3 are the very variables that we added such that we can capture such that we can capture the number of additional staff in charge of product 1, 2, or 3 for specific hours of the day. So initial value, obviously the default value of these variables is all 0, and that's why in the base case scenario that looked like as if we haven't added any staff. However, in this scenario, I want to increase the number of staff. So let's assume for the sales, for a specific number of hours, we want to hire 2 more sales staff. So for the initial value of these variables, I'm going to put, for example, number 2. Okay, so that will guarantee that when I start the simulation, the new sales variable starts with number 2. That will mean that the simulation will assign 2 more staff to this schedule in a specific hour. And if you want to have a closer look, if you look at the schedule, And if you go to the sales schedule, the schedule that we defined, sales schedule, if you click on that, you see the new sales was used here. So for some specific hours during the day, just for 4 specific hours during the day, we wanted to increase number of staff, and then we added these new cells. So we want to increase the number of sales staff from 5 and 6. So we want to add maybe 2, 3 more staff. So we added these new variables, and then and the initial value of this new cells was 0. So that was the base case scenario. But if I want to hire more sales people, I can increase the variable new cells. And if I increase it to 2, like what we did right now, that means for this time period in the simulation, I will have 5 plus 2 or 7 sales staff working. So that's the meaning of the changes that we made. So let's go back to the variable again. So for the cells, for the new cells, I increased the value to 2. That means I will hire 2 more people in those specific hours. And let's assume for technical staff 1, I'm going to change the initial value, which is automatically 0. I'm going to change it to, let's say, 1. So I'm going to just hire 1 more person in charge of the technical questions related to product 1. So those are the changes that I want to make. And also let's go to the resources for the trunk lines. So remember we had 26 trunk lines. So let's assume I want to have 29 of them. So I'm going to have 29 trunk lines. And remember the total cost that we had calculated at the end had the cost of the trunk lines as well. So I want to have 29 trunk lines instead of 26. And I want to see how these changes is going to affect the total cost and percentage of rejected calls in the model. So before you run the simulation model, make sure to go back to the statistics. This is very important. Go to the statistics, click on the total cost, and here change the name of your data file. Otherwise, when you run the simulation model again, you are going to rewrite the base total cost data file. However, I want this to be saved in another data file. I'm calling it alternative 1 total cost .dat. The reason is that if you want to have a comparison between the base case result and the alternative 1 result, you want to have them as 2 different data files. If you do not change the data file and run the simulation model, the simulation will overwrite the previous data file, so you won't be able to compare the 2 scenarios if you want to. I'm going to do the same for percentage of rejected calls. So here I'm going to change it instead of base. I'm going to say this is alternative 1 calls rejected. And then here I'm going to run the simulation. And if I look at the folder in which the model has been saved, I see that now I see both base cost and base rejected calls data files, and also see alternative total cost and alternative rejected calls data files. Both these additional data files were created as well. Now I can go back to the output analyzer window and plot the confidence interval for both. So here, let's say I'm going to analyze, and still let's assume I want to develop confidence interval for 1. So here, I'm going to delete the data file that I already have. I'm going to add the base total cost that I had lumped. Okay, and I'm going to add another data file, and this data file I'm going to add alternative 1 total cost, and again lumped. Press OK, and this is going to be a 90% confidence interval for total cost. And I want to keep it at 90%. You can change it to 90%, 99%, 95%. So I'm just going to keep it at 90%. Then I press OK. So you see this, I put 2 different confidence interval in the same graph. However, since the scale of these 2 confidence interval are the same, both of them are around thousands, the graph doesn't look like the previous one that we had when I put the cost and percentage of rejected calls into 1. So still we can see both graphs clearly, and it's fine. So here on the top, I see the percentage of rejected calls for the first scenario, so that's the first data set that I chose. Remember, the first data set that I chose was for the base total cost. So as we can see, the average cost for the base scenario is less. The second data file that I chose was for alternative one. So the average of the cost per day for the alternative scenario, when we added more resources, has increased, and obviously the confidence interval has changed as well. And the reason that this cost has increased is that because we added more staff and we increased the number of trunk lines, right? There was cost associated with adding more staff and adding trunk lines, and that's why we see the cost has increased. Obviously the waiting time in the system has decreased, but apparently the decrease in the waiting time in the system hasn't been that much to offset the increase in the cost because of adding more staff. So here you see again the average cost for each one of them, the standard deviation, the confidence, half of the confidence interval, and the minimum and maximum for two. And in both scenarios, we have 10 replications or 10 samples, and that's what we see here. I also want you to pay attention that this point, the red line and the red dot shows the average. This point shows the lower bound of the confidence interval. This point shows the upper bound confidence interval. And here, the point that you see here, this red line that you see here, and then you see also here at the top, shows the minimum and maximum. And you can see the minimum and maximum here. So this is the minimum of the total cost across all the 10 replications that we have observed, and this is the maximum of total cost across these 10 replications. So this graph not only shows the average of cost across the 10 replications, their lower bound of confidence interval, upper bound of the confidence interval, the minimum across 10 replications, and the maximum across 10 replications. So those are the things that we see here.